So hello everyone. We will get started with this interactive session for the basic electronics NPTEL course. My name is Mahesh Patil, and the way we will do this is I will first go through a few problems which I have prepared. If you have any questions related to those problems or general questions, please post these on the YouTube chat, and then we can take those one by one. But to begin with, we will look at a few problems which are based on things that you have covered so far in the first 2 weeks of the course. All right, so I'll share my screen and we'll get started. All right, so here is our first problem. It is based on various things that we covered: network theorems, superposition, Thevenin's theorem. And the problem statement is a circuit is given. We have to find the Thevenin resistance and the Thevenin voltage as seen from the port AB. The second question is to find the maximum power that a resistor connected between A and B can dissipate. And the third question is, once we are through with this first part, then use that information to find the RTH and VTH for some other values of the sources, the voltage source and the current source. So these are the three questions we will take up. If you have any questions, you can enter in the chat box, in the YouTube chat box, and then I will take those up. It will take a few seconds of delay, so just be aware of that. But I will eventually see those questions and answer those queries. All right, so let's look at this first question. Find RTH. In this circuit, we have two independent sources, a voltage source and a current source, and then there are no dependent sources here. So it's a very fairly straightforward case to handle. To find RTH, what we do is we deactivate the voltage source, independent voltage source, and deactivate the independent current source. And when we deactivate an independent voltage source, essentially we replace that with a short circuit. Like that. And when we deactivate a current source, then we replace that with an open circuit. Like that. And then we look at the network from the port AB. And of course, in this case, it's pretty straightforward. We see that R1 and R2 come in parallel, and then that combination comes in series with R3. So our answer is simply RTH equal to R3 plus R1 parallel R2. R3 is 1K and R1 parallel R2 is 1 times 4 by 1 plus 4 kilo ohms. So that is 0.8. So that is the net result is 1.8 kilo ohms. That is our RTH. Right? All right. So now in order to get VTH, what we need to do is to find the open circuit voltage between A and B. So this is the voltage of interest. And we can do that using superposition because we have two independent sources in this case, and any current or any voltage, including VOC, can be obtained by superposition. So let's do that. Okay, what I will do is I'll make a copy of this. All right, and we will consider two cases. Case one, where the independent voltage source is active and then the current source is not active. Case two, all right, let's just start doing that so it's very clear. So case one is where only the voltage source is active, current source is not active. Case two, where the current source is active but the voltage source is not active. And so we deactivate the other source. The current source in this first case is an open circuit, and the voltage source in the second case is a short circuit, like that. And we will then call this VOC as VOC1, case 1, and this VOC as VOC2, case 2. Right. Now in this first case, VOC is simply the voltage across R2, because there is no current through R3, and so there is no voltage drop across R3. And that voltage drop, this one here, is simply R2 by R1 plus R2 times 5 volts. So VOC1 would then be R2, which is 4K, divided by R1 plus R2, which is 5K, multiplied by 5 volts. So that is 4 volts. So that is what happens in case 1. All right, let's look at case 2. In this case, we see that R1 and R2 come in parallel. Once again, R3 does not conduct any current, so therefore there is no voltage drop across R3. And since R1 and R2 are in parallel, let's just redraw the circuit. So what I'll do is I'll just move this, and then we draw this resistance R1 in parallel with R2. So this is R1, 1K, and then we'll remove it from there. We just moved it without really changing the circuit. It is still in parallel with R2. Right? So that's how the circuit looks like now. And once again, we are interested in this VOC, which is this voltage drop. Voltage drop across R1 or R2. And that is simply given by 5 milliamps times R1 parallel R2. So that is 5 milliamps. R1 parallel R2 is 4 by 5K. And so that also turns out to be 4 volts in this case. Right? So VOC net is, by superposition, is the sum of VOC1 and VOC2, which is 4 volts plus 4 volts. That is 8 volts. So that is our answer to the first question, RTH and VTH. All right, let's look at the second question now. Find the maximum power, right? And this is of course covered in the slides. So what do we do for that? We connect a load resistance, and we have seen that this load resistance has to be equal to RTH for the power drawn by RL to be maximum. And in that case, the current is of course VTH divided by RTH plus RTH, right? So that is 2 RTH. That is the current through RL. So current squared, and that multiplied by RL, and RL itself is RTH. So that is the maximum power that we are expecting. And so in other words, it is VTH squared by 4 RTH. You can calculate that number, and I'll just write the final answer here. It is it's about 8.9 watts, or milliwatts rather, because RTH is in kilo ohms. Okay, so that's question 2. Straightforward. Let's look at question 3 now. Okay, question 3 says find RTH and VTH for some other values of the source voltage and the source current, right? Okay, so here we can make use of superposition, and let's see how. All right, so this circuit that we are considering is like any other linear circuit, and therefore any quantity in this circuit, any voltage or any current that is given by a linear, will be linearly dependent on Vs and Is, right? So we can write this equation here. VAB is K1, some constant K1 times Vs plus some constant K2 times Is. How we can actually calculate these values of K1 and K2, and that is using our results of part A. We know that VOC1 was 4 volts when Vs was kept, that is Vs was 5 volts, and Is was removed, so that is Is was 0. So what is that telling us? That is telling us that VOC1 is the same as VAB1. So that is 4 volts, and that is equal to K1 times 5 volts and plus K2 times 0, because Is was 0 in that case. So this gives us the value of K1, well, that is equal to 4 by 5, and that of course does not have any dimensions. Similarly, when we had the second case, we obtained VOC again as 4 volts, and that happened when Vs was made 0 and Is was kept at its given value, which is 5 milliamps. Now we substitute again in this equation. We write VOC2, which is the same as VAB, as 4 volts equal to K1 times, this is 0 now because Vs is 0, plus K2 times 5 milliamps. So this is telling us that K2 must be equal to 4 volts by 5 milliamps. So K2 has units of resistance, but we can leave it at that. All right, so now our question says that Vs has changed, Is has also changed. Vs has changed to 2 volts, Is has changed to 2 milliamps. And then what is the new Thevenin voltage? So the new Thevenin voltage, of course, is nothing but the open circuit voltage now, or that is the same as VAB when you don't connect anything there. And that is given by K1 times Vs. K1 we know is 4 by 5. Vs, the new Vs, is 2 volts plus K2 times Is. K2 we know already, 4 volts by 5 milliamps. And the new Is is 2 milliamps. Right. Okay, so that comes to, let me check. Okay, that comes to 3.2 volts. So the Thevenin voltage in the second case with these new values of sources, which is the same as the open circuit voltage there, is 3.2 volts. And of course, the Thevenin resistance does not change. because that is not dependent on the source values. All right, so very quickly, let's just verify whether our results are correct, and that we will do using simulation. So here is the same circuit, and first let us plot. This is our load resistance. Right now, it has some high value, one giga ohms. What we're going to do is we're going to let that vary, and we're going to plot the power absorbed by that resistance as a function of RL, right? So PL versus RL is what we will plot. And this kind of plot you would also see in one of the slides that you would have seen in the first week. So let me run the program and choose RL as the x-axis, the power of RL as the y-axis, and plot. So here is the plot. And this tells us two things. One is that the maximum power is this number here, which is like 8.9 milliwatts. You can just see that axis here, y-axis. That value is about 8.9 milliwatts, and that's indeed what we got. That's one piece of information. Second, that will happen when RL is equal to RTH. And by zooming on this plot, we can see that that is happening with when RL is equal to, this is 1500, this is 2000, this is 2500. So 1.5k, 2k. So and this point here is 1.8k. So it's maximum. The power, the P max happens at RL equal to 1.8k, which is the Thevenin resistance. So all this, of course, is expected, and we are simply verifying it. There are more things we can do. Let's look at the circuit again. All right. So what we can check here is we cannot check the Thevenin resistance directly, but we can check the open circuit voltage and the short circuit current. Now the open circuit voltage, of course, is the same as the Thevenin voltage, which we got as 8 volts. So that would happen if this resistance is very large, and that is let's say 1 giga ohm is large enough compared to all of these other values. And let's run this simulation and see if that open circuit voltage is indeed 8 volts, right? So this is the first entry is VRL, voltage across RL, and that is indeed 8 volts, right? 7.999 and so on. Okay, so that is what we expect. Second, we can verify whether the short circuit current is correct. So short circuit current then would be VTH divided by RTH, and that turns out to be some 4.44 milliamps. So let me make this very small. So instead of 1 giga ohm, let me make it 1, let's say, micro ohms, U for micro. And now run the program again. And now you can look at the current. So the current is indeed 4.44 10 to minus 3, 4.444 milliamps, and that is what is expected. All right, so this is how you can use circuit simulation also to just check sometimes our understanding. All right, so let's okay, there is a question from Abhishek Kumar. He says, please upload this video because my net is not working and I'm not able to attend it live. So that is fine. The answer to that is this is going to be available on YouTube, and your course site will also have that link. So you don't need to worry about recording it separately. Okay, so let's go to the next question. And that is based on RL and RC circuits. In particular, this is an RC circuit, and you would have done some of these calculations in the second week, right? Okay, so what is this question? So there's an RC circuit, there's a single capacitance, and that is of course the case that we have handled also in week 2. But apart from that, there are some other resistors and 2 voltage sources, and there's a switch which opens at t equal to 0. Question 1, what is the time constant after the switch has opened? So that means after t equal to 0. So let's do that first. So let me just copy this circuit here. All right. So what we want to, so the switch is open now. So we can in fact remove it. Right. And now we want to look at this circuit from the capacitor. So we want to look at this circuit from here. So let's from the capacitor. And we should deactivate the independent sources. In this case, there are 2 independent sources, the 2 voltage sources. So let's deactivate those. That means we'll replace those with short circuits. So short circuit there and short circuit there. Right. And now we calculate the Thevenin resistance as seen from the capacitance. And this circuit is quite similar to what we saw earlier. So what is RTH in this case? It is R1 and R2 are in parallel, and that combination is coming in series with R3. All right, so this is like 50 parallel 200, so 50 times 1 parallel 4 plus R3 is 100 ohms. 50 1 parallel 4, where 1 parallel 4 is 50 times 4 by 5, and that plus 100 ohms. Okay, so how much is that? 140 ohms. So our tau is that R Thevenin as seen by the capacitor multiplied by the capacitance value, which is 1 microfarad. So 140 times 1, and that will be in microseconds. Right? So in other words, it is 0.14 millisecond. Okay, and why is tau important? Because we know that our transients will basically die out in about 5 time constants. So we expect the transients to die out in 5 tau, which is 0.14 times 5 or 0.7 milliseconds. Right. So remember this number when we look at simulation results. We will be able to actually verify that this is happening. Okay, just give me 1 minute. I need to check whether there are any questions. Okay, so there are no other questions. Fine. So that is the answer to question A. And now second question is plot V1 of t and Vc of t. V1 is this voltage here across R2. Vc of course is the voltage across capacitor. So this actually involves several things, and you would know by now what all it involves. So we need to first consider the situation where the switch is not yet opened. So that means t equal to 0 minus. Okay, so t equal to 0 minus. Let's consider that situation. What is happening in at t equal to 0 minus? The switch is still closed, and therefore this entire combination R1 BS2 in series is basically bypassed, and so the circuit essentially reduces to this here. Right? So that's happening at t equal to 0 minus, and we can say that V1 then is simply 10 volts. So V1 is 10 volts, and VC is also 10 volts, and that is because this current is 0 in steady state. So we are at 0 minus, and the circuit has been like that for a long time. So therefore the dvc dt has become 0, and therefore the current, which is c times dvc dt, has also become 0. If this current is 0, then this voltage drop across R3 is 0, and therefore therefore VC and V1 are the same, and that's how we get VC equal to 10 volts. So that is the situation at 0 minus. Okay, let's look at 0 plus now. What do we know about the capacitor? We know that the capacitor voltage does not change instantaneously, and therefore this voltage will stay the same as it was at 0 minus. So that is 10 volts. Right? And now the switch has opened. Right? So the switch is gone, and so therefore this circuit basically has reduced to that. All right, now how do we handle this? Straightforward. Uh, this is 10 volts, right? So it's as if we have a voltage source there, and it's as if we have a voltage source there, which is 10 volts. So let me get rid of this part. That just makes things easy to see, right? All right. And these two voltage sources, VS1 and VS2, are in series, and they can be combined. So what I will do now is to remove this VS2 from there, and just make this 10. Instead of 10, I'll make that 20 volts. This is now not 10 but 20. Right, so that's another change I'm making. And this voltage source is now gone. So we just replace that with a short circuit. So that's our circuit, and probably the easiest way to uh, solve this is to take this as a reference node. In that case, this is V1, and now I can write KCL at this node here, this node, right? So what will that tell? What will that give me? This node voltage is 20 volts. This node voltage is 10 volts. So the three currents now will add up to 0, and that gives us V1 minus 20 volts divided by R1. That's one current, plus V1 by R2. So we have talked about this current and this. So the V1 by R2 is that current, plus this current, which is V1 minus 10 divided by R3. Right. So this must add up to 0, and that gives us the value of V1. I'm not going to do all the algebra here, but I have the value here, which I will copy from my notebook. that turns out to be 5.7, nearly 5.7 volts. Yeah. All right. So the answer to second the second set of points that we need at 0 plus, VC is 10 volts and V1 is 5.7. Okay. This was the first one. 0 at 0 minus this one, and this is the second at 0 plus. And to get a complete picture, we also need to figure out what's happening at as t tends to infinity. So that is the third part. Remember these numbers, right? V1 equal to Vc equal to 10 at 0 minus, Vc is 10 at 0 plus, V1 is 5.7. And now let's consider t tending to infinity. As t tends to infinity, the all currents and voltages will become constant, and therefore once again C dV C dt will become 0. So the capacitor behaves like an open circuit, and that's what we have in front here. Once again, we have combined these two voltage sources into a single source, and that's what the circuit looks like. This case, it's V1 is simply given by voltage division. This current is 0. This is 0 because that's open. That's an open circuit there. And so V1 is simply R2 by R1 plus R2 times 20 volts. Okay, so what is that number? Okay, that's easy enough to calculate. So R2 is 50 and R1 by R1 plus R2 is 250. That multiplied by 20. So that is 4 volts, right? Okay. V1 is 4 volts. What about VC? VC is also 4 volts because there is no voltage drop here, that current being 0. So V1 and VC are equal, and that is our third condition. V1 equal to 4 volts, VC equal to 4 volts. And this happens as t tends to infinity. All right. So that's really all that we need to plot V1 and VC as functions of time. And of course, the additional information which we already have is that the time constant, or rather the 5 times tau, is how much was that? 0.7? 0.7 millisecond, yes. So we will see transients as the switch opens at 0, but those transients will vanish in about 0.7 milliseconds. So putting this all together, we expect something like this, right? So VC at 0 minus is 10 volts. VC at 0 plus is also 10 volts. VC at infinity is 4 volts. This is 4. That is what we expect for VC. And this transition happens in 5 tau or 0.7 milliseconds. V1 was 10 volts to begin with at 0 minus. At 0 plus, it jumped to 5.7 volts. That is this point here. And eventually, as t tends to infinity, it goes to 4 volts. So that is what V1 looks like. So let's quickly check this against simulation. That is the circuit, right? Okay, now there is a switch which is driven by some step here, and that the step basically is going from 1 to 0, and that means that switch is opening at equal to 0. The rest is pretty straightforward to understand. Okay, so let's run this simulation and just verify that verify V1 and VC. Verify that those plots indeed look like what we expected. So VR2 is the same as V1 in our figure, and VC is VC. So that's what we are, right? And this is exactly what we saw in this picture. You can see that this is our 0. This is 0.002 seconds. So that means 0.2 milliseconds. This is zero point 0.4 milliseconds. This is 0.6 milliseconds. So in 0.7 milliseconds, these transients are basically dying out, and that is what we would expect. The capacitance voltage, the red one, does not show a jump at 0, but the voltage across R2 does show a jump from 10 volts to 5.7, as we would expect. Okay, so that was question number 2. So there's a question. Let me just answer that. Okay, so Abhishek Kumar is asking, please discuss about final exam. What type of questions like objective or subjective will be asked in the final exam? So the final exam would generally be all objective, multiple choice, and but you'll have to work out things. So things like what is VC as t tends to infinity, for example, right? So that, and then you will have 4 choices. Uh, yeah, there are no subjective questions. There are only objective questions, and they're all based on uh, things that you learned in your course. There is one more question from Ramya Ashok. Subject is difficult for me to understand. Okay. All right. So this we have to take offline, because in this forum, let's only deal with technical questions. But if you have any other non-technical questions, you can write an email, and then we can try to answer those by email. All right. So before we close, let's just look at one more question, which is also based on things we've already done. And this is a little more complicated than the first question we saw, right? And it's complicated because we have this dependent source here, right? What is the what are we trying to do? We are okay. What are we asked to do? We are asked to find the Thevenin resistance and the Thevenin voltage as seen from AB, and we are also asked to find the power absorbed by a load resistance connected here, if that load resistance is 100 ohms. Okay, so these are the 2 questions that we want to answer. All right, and now why is it more complicated than the first circuit we saw? That is because there is this dependent source here, and that's controlled by this current here, I1. So if that is I1, this current is 1.5 times I1. So this is a current controlled current source, right? CCCS. Okay. Now in this case, we cannot find RTH simply by deactivating the independent sources, because there is this dependent source also in the circuit. So what we can do is find the open circuit voltage, POC, shown here. That means don't connect anything across AB. Figure out what that voltage is. Find the short circuit current by just shorting A and B, figuring out what that current is, and then after that we can get RTH equal to VOC by ISC. And the Thevenin voltage, of course, is simply equal to VOC. So once we have VOC and ISC, then we have basically solved this part, right? So let's see how to get VOC. All right, so if nothing is connected across AB, then what it means is this current is 0, right? And this 1.5 I1 will go like that, right? So this will be 1.5 times I1. Now this 1.5 I1 is going like that. Of that I1 is going like that. So this current must be 0.5 times I1. Right? simple KCL. And now we can get somewhere. What we can do is write KVL in this loop here. So, and then we can immediately find what I1 is. So let me take voltage drop as positive. So I'll first get this voltage rise of 20 volts. So that comes with a negative sign. Then I get 0.5 I1 times R1. That also is a voltage rise. So that will be 0.5 I1 times R1. That also comes with a negative sign. Plus this voltage drop across R2, and that is R2 times I1. So the only unknown in this equation is I1, and we can figure that out by solving this. So let me check what I've got for I1. Yeah, I1 turns out to be 1 by 9 amperes, which is 0.111 ampere. So remember that. Okay, I1 is not what we really want. What we want is this open circuit voltage, right? And what is that? So we can follow two approaches. One is we can go like this. So we know that voltage drop now because we know I1, and then we can go like this, and that's it, right? So then we get VAB. That's one. The second approach we can follow is go like this. We know this voltage drop. We know the voltage drop across R1. We also know the voltage drop here, and come back here. So that's the second approach. Of course, both of them will give us the same answer. So we'll just do the first one. So I can say, yeah, I can say the open circuit voltage now is, okay, the voltage drop across R3 first. So 1.5 I1 times R3 plus the voltage drop across R2. That is R2 times I1. Right? Okay, we can substitute values and find out all that. That is 38.9 volts. That is the same as the open circuit voltage or the threshold voltage. Right. All right, so that is simple enough. Now let's look at the short circuit current. And once we have the short circuit current, then we can find RTH. So let's look at this circuit. In this circuit, what is happening is this, suppose I take this as, a reference node, and let me call this as some V1. With respect to this reference node, I already know that this is 20 volts. And this node here is actually at 0 volts, right? Because there is the short circuit here. So, and that short circuit is connecting node A to ground. So our circuit is actually quite simple. It is like this. Right? This is R1. This is V1 here. This is R3, and this is R2. And we can find V1 by writing KCL. V1 minus 20 volts divided by R1 plus V1 by R2 plus V1 by R3. That should give us 0. So that gives us V1. And of course, we are still not done. We need to get to IAC. But let me write down the value of V1. V1 turns out to be 12.5 volts. You can verify all these calculations later. All right, so we have V1 now, and we want to get to the short circuit current, IAC here. Right? So what is that? If we have V1, we can find this current, right? We can find I1 because that is simply V1 divided by R2. So we know I1. And then ISC is simply the sum of those two currents. So ISC then is V1 by R3, this current, plus this current, right? Plus 1.5 times I1. And I1 is this times V1 by R2. And V1 is already known, right? Okay, so just evaluating that gives us 17, so that gives us 0.219 amperes. 0.219 amperes. And now we can find RTH. VOC is known, or the VTH is known. I short circuit is known. And so just take the ratio and you get 178 ohms as RTH. Right? So now we have our equivalent circuit. So the next question is pretty straightforward. We want to find the power absorbed by this RL if RL is 100 ohms. So with this number we already know 38.9. This we already know 178 ohms. So we can find this current I equal to whatever 38.9 divided by 178 plus 100. We can do that. And then once we have I, the power is simply I squared times RL. Right? So the answer is 1.96 watts. Okay. All right. So let's verify this also by simulation. So we will check for two things. One is the open circuit voltage, 38.9 volts, and one is the other is the short circuit current of 0.219 amperes. So let's do that. Okay, so here is our circuit. This VS1 is just 0, so there is a short circuit there. And this is 1.5 times that particular current. That's how this syntax is. This is 20 volts, and this is our RL, right? So RL, let's make RL very large. If we do that, then the voltage across that RL will give us the open circuit voltage. So let me make RL equal to, let's say, very large value like 1 giga ohms, 1 G. And now if I run the solver, I should be able to see VRL as our VOC, which is like 38.9 volts. That's indeed what we have. VRL is 38.9 volts, right? 3.89 10 to 1, so 38.9 volts. Okay, next, if we replace this resistance with a very small resistance, let's say 1 micro ohm, 1 U, then the current through that resistance should match our short circuit current, which was 0.219 ampere. So let's verify that also. IRL is what we're looking for. IRL is 2.1875 10 to minus 1. So it is 0.219 ampere. Okay, while we are at it, maybe you can also do the last part. Let's make this 100 ohms and see if we get if the power absorbed by this resistance is what we got at 1.96 watts. So let's run the solver, and okay, it's here in this file. That's 1.96 watts. All right, so in this way you can use simulation also to check out things, check if your answers are correct. Let me see if there are any other questions. Oh, sorry, I think I missed this. Why don't we consider I times R2 voltage? Uh, let me see. I times R2. The question is not clear to me. I times R2. Yeah, I would request, what's the name? Darsai. Okay, the student's name is Darsai. Okay, for VTH. Okay, so for VTH, why don't we consider I times R2 for VTH? Okay, so we are talking about this calculation here. Okay, so I'm not sure if I understand this correctly, but let me explain once again what we have done. First, we found I1, that is that. And then once we know I1, we know all the voltage drops, right? And what we are looking for in particular is the voltage difference between A and B. So we need to have a path from A to B. Uh, uh, Along which we know all the voltage drops. And one of those paths is this, right? So that we go like this, R3 and then R2 and to B. So that is what we have done. 1.5 I1, this current times R3 plus I1 times R2, that voltage drop there. So that is this. So that voltage drop across R2 is already taken into account there. So that's one way we can look at this, or we can compute VAB. The other way is we can go like this, right? So we know this voltage drop, we know this voltage drop, we know this voltage drop, right? And that's it. Then we are back to B. So that's the other option, and you should get the same answer. I hope that is clear. If not, you can just post, just write an email. Okay, there's a question about phasors. Why you first converted sine to cos and then changed frequency?